What's a force? A force is defined simply as a push or a pull. That's it. There's nothing really more complex than that. So how do we represent a force? Again, we do something really complex. In other words, how do we draw them? We just draw an arrow. The longer the line, the bigger the force. And the arrowhead tells us which way the force is acting. Now, we call this arrow a vector. So, we have two kinds of numbers. We have vectors and we have scalars. A vector, as you can see, has a magnitude and a direction. A scalar has only a magnitude. So let's look at these examples down here. 20 newtons north would be a vector. 20 newtons, that's our magnitude. That's how big the line would be on that arrow. Okay? If I had 40 newtons, it would be a longer line. If I had 10 newtons, it would be a shorter line. North, I hope you can see, that's our direction. That tells us which way it's going. So for vectors, which way something is working makes a difference. A scalar has only a magnitude, only the number. So there's our scalar on the bottom, 10 degrees Fahrenheit. It doesn't make any sense to say 10 degrees Fahrenheit north. It would make no sense to give it a direction. So a scalar has no direction. It has only a magnitude. Okay, so when we're talking about forces, we can have balanced forces or unbalanced forces. If we have a lot of forces working on an object, or at least more than one like we have here, they can be balanced. If you look, they're pushing in opposite directions, but notice how the length of these lines is the same. That means their magnitudes is the same, right? So that means these forces are balanced. In other words, they cancel out. That's the way you would think about it. And so there would be no acceleration in this case. Okay, now it doesn't say whether the box is moving or not. It just says that there's no acceleration, which means the speed and the direction is not changing. Now, if we have unbalanced forces, as in the case of this truck, then we have an acceleration. That's why we have up on top, the truck speeds up in this direction, because we have some unbalanced forces going on. So balanced forces cause no acceleration, or in other words, we get no acceleration if we have the forces balanced. If the forces are unbalanced, then we have acceleration. So Newton's laws. Newton has 3 laws of motion. You know most of them, or at least we can get them out of you, but you may not know them right off the top of your head, so let's go through them. The first one, an object will remain at rest or in uniform motion in a straight line unless acted upon by a net force. So that's what's happened to this guy. What's happened is his motorcycle has hit the tires, but he didn't have anything to hit. He had no force act upon him, as you can see right here. No force acted upon him. And so he continues in a straight line at uniform motion. That means his speed is constant. There's no acceleration for this guy. He just goes off the bike in a straight line. That's what Newton's first law says. It says objects want to stay the way they are, really. Second law, this is the one that you use the most. You can see you've got this guy pulling here on this big jet. Newton's second law says that big jet is not going to accelerate very much, because I don't care how hard this guy pulls, he's not going to pull with a whole lot of force. Now, if we turn those big engines on, that would be a much bigger force on this big jet. So the acceleration would be very, very large. And that's how we get it to fly. We apply a large force to that mass, and we get him to fly. Now, if we put those engines all on this guy who has a little mass, then he would take off way, way faster acceleration than that jet. He could fly almost immediately, where the jet takes time to get up to some speed because it's got a much lower acceleration because of its mass. Now, we use a formula for this that we usually represent as F equals m times a. Force equals the mass of the object times the acceleration of the object. This is the formula you'll use all the time in this class. It will haunt you in your dreams. It will be the one probably that you get stuck on the most because we use it so often. But that's Newton's second law, is force equals mass times acceleration. Now we need to talk about units for a minute here. If we have a mass in kilograms and an acceleration in meters per second squared, that means 1 kilogram meter per second squared is our force. Now we get tired of writing all this kilogram meter per second squared out, so we change it and we just call it a Newton. 1 Newton is 1 kilogram meter per second squared. Now it's important to remember this, because when we cancel our units out, you're going to have to remember that inside of this Newton is all these units, this kilogram meter per second squared. Okay, so you want to make sure you've got those units down. Now, his third law. This is the one most people know. For every force, there's an equal and opposite force. Okay? So if your finger pushes on the wall, right here, that's the blue one, then the wall pushes back on the finger. That's the green one. Now, the trick with this, and the thing you need to really realize, is the green force is acting on the finger, and the blue force is acting on the wall. So they are not acting on the same object. They are acting on opposite objects. So when we talk about something like whether you break that wall, we look only at the blue force. So if the blue force is bigger than the wall can handle, we would break through that wall. We don't look at the green force. We look only at the force working on the wall to see if the wall breaks. Now, if we want to know if that finger breaks, if you're doing like a karate punch, we want to know if that bone's going to be in trouble, then we look at the green force. And if that green force is greater than what the bones can handle, then we might be in trouble. Okay? So Newton's third law says equal and opposite. That's the law. And that's what most of you really know, but it's the third law. Okay, now when we have multiple forces working, we talk about something called a net force, which just means we add up all the forces. And we have to worry about the direction. So right here, on this top one, you see 10 newtons to the right, 10 newtons to the left. So what we would say is that it is 10 newtons here in the positive direction, plus 10 newtons in the negative direction. So we have 10 newtons plus a negative 10 newtons. That's a net force of 0. Now if we look at the second one, we have 10 newtons in the positive direction, 10 newtons in the positive direction. So 10 newtons plus 10 newtons is 20 newtons in the positive direction. So that's where we get a net force of 20 newtons. Now this bottom one is kind of wrong. I don't like it that much. We have 8 newtons in the positive direction, 10 newtons in the negative direction. So that means our net force is 2 newtons in the negative direction. So this answer, it should really be 8 newtons plus negative 10 newtons, and this should really be negative 2 newtons. So that's what we've got there. So that's what we're doing. When we talk about our net force, we're just adding up all the forces working on that object. Sometimes we call it the sum of the forces. That's the way I will always write it. Thanks for listening.